Alright, today let's do some applications of integrals. So the first one we're going to do, it's a cross-sections problem. We have a region R, which is the region in between the function y equals x squared and the x-axis up till x equals 1. So this will be R. And so the question is, what's the volume of a solid with a base R and square cross-sections? And then what about semicircles? What about hexagons? So first, we're just going to do setups for these. The first one is a square cross-section, so that's just going to be r squared. So we have our integral. Sorry, let's write that a little nicer. It's our integral from 0 to 1. Our function, which will be our r here, is going to be x squared, and this is going to be whole squared dx. And okay, so next up, we're going to have semicircles. So the equation for semicircle is pi r squared over 2. And so the semicircles will be the integral from 0 to 1 of 1/2 times, or pi over 2 times r squared, which once again will be x squared. However, it'll be divided by 2 because x squared will be the diameter. And then finally, we have we have hexagons, and so that'll be the integral from 0 to 1. If you guys don't know this, the area of a normal hexagon or a convex hexagon is 3√3 over 2 times a squared, which a is the side length. So in this case, we're going to have 3√3 over 2. Our side length is x squared, and we're going to square that. And that is the answer to that problem. Alright, next up, we have the volume of a solid formed by the revolution of r about the x-axis. So this is a disk problem, a disk and washer problem. And our y is going to be the square root of x squared minus 5x plus 9. So our setup here is we know it's going to go from 0 to 5. So the integral from 0 to 5 of pi times r squared, which will be, r squared is going to be x squared minus 5x plus 9. This is just because we're treating each revolution as a circle. Just going to add that up, dx, and this computes to be about 75.9. Yeah, 75.9. All right, moving on. We have the volume of a solid formed by r revolving about the x-axis. And our equation here is y equals the square root of 2x squared minus 6x plus 19. So this is going to be a washer problem. And the way we're going to do this is first we're going to solve for y of 10. And y of 10, plug that in, y of 10 is going to be about 8.038. And so then solving for our area is going to be, we're going to have, let's see. Well, the area is going to be the entire thing subtracted by what's inside, right? So that area is going to be pi times r squared, which is 8.038 squared, times the height in this case will be 10, as it's a cylinder. And what we're going to subtract from it is whatever's inside. And that is going to be the integral from 0 to 10 of, this will be pi r squared, so 2x squared minus 6x plus 19 is going to be r squared dx as usual, and this will compute out to about 1705.1, and that will be the answer to that problem. Alright, finally we have another problem, which is going to be the area between curves. And our two functions are going to be y equals x to the 8x minus 3 and y equals 7x minus 7. So if you want to visualize this, give me a second. If you want to visualize this, let's say this is our graph. Both these functions are probably going to be in the negatives early. So it's going to look something like that and that. Or actually, it might be something more about like that. And so if that's our function, we can see that 7x minus 7 is going to be on the top. But just to be safe, we can use absolute value. So this will be the integral from where they intersect. So we just set the equations equal and we get they intersect at 0.583. 0.583, and they also intersect at 1.165. And we're going to have the absolute value of x to the 8x minus 3 minus 7x minus 7 dx. And this turns out to be about 0.739. And that is the answer.